So, welcome everybody. Our speaker today is Jun-cheng Wei from UBC in Vancouver, and he will talk about singularity formations in some geometric flows. Thank you very much for coming, and please go ahead.
Okay, I want to thank the organizers for inviting me to this online seminar, and I'm very happy to see old friends and also meet new friends online, and hope when the pandemic is over, we can meet in person. And this is, I hope next year. Yeah. All right. Okay. So I'm going to talk about some recent work on singularity formations in some geometrical flows. So basically, I'm going to talk about three flows. The first one is the Harmonic Map Flow. This is the classical flow, Harmonic Map. The second one is two Half-Harmonic Map Flows. Okay, sorry. And so I'll talk about some different singularity formations in these two Harmonic Map flows. And finally, I will discuss recent work on Yang-Mills singularity formation for Yang-Mills Hit flow in R4. Okay, so let me start with the Harmonic Map flow because this is a classical flow. And in the first part, I want to introduce the method that in constructing all these singularity formations, and then we're going to see how we can apply this method to other flows. So we start with the classical Harmonic Map flow, and so this is a map from any R2 to S2, and the Harmonic Map flow is just a parabolic flow for the diffusion energy function. Now this more general Harmonic Map heat flow between two embedded Riemannian manifolds and M and N, and then you can write down the equation. Oh, okay, just one moment. You can write down the equation, but the simplest non-trivial case, aside from the heat equation, is when omega is R2 and the dimension is S2. Okay. And so this becomes a Harmonic Map flow. And so this Harmonic Map flow is also a basic toy flow, basic flow in many applied problems, such as nematic nickel crystal or Landau-Lipschitz Gabor equation for ferromagnetic. Okay, so let me start with Harmonic Map flow. So there are many results. So this is a classical equation, and this has been extensively studied. And there are lots of activities in the 80s and the 90s. And the local existence by Yields and Sampson. So for global solution, this was initiated by Sachs and Wallenberg, and then Stewart 95 complete the Harmonic Map flow in dimension 2. So he proved the existence of global weak solution. And then Chen and Stewart in 1989 extended to higher dimensions. Okay, so this exists a global weak solution. Now it does not exclude blobs. Even for global weak solution, you may have blobs. So a blob for Harmonic Map means that the gradient goes to infinity. Right? So there are many results on general description of blobs by Yost, Parker, and Qingjie, and Dean, and Tian, and Torbin, and so on. And you have energy identities, and also the bubble tree convergence for approximate Harmonic Maps. And for blob in finite or infinite time, you also have bubble convergence by Qingjian and Gang Tian and many other people like Pang Huanin and Chang Wang and Tuoping. Okay, so the question is what, and you have a general description of a blob. So when you say blob, you're going to say outside, I trace, which is C infinity, and then you have a bubble, and this bubble is nothing but a stationary harmonic map. So this is a general description of a possible blob for harmonic map flow. So the question is, do we have the existence of bubble solutions? And this has been a intensive study in the 90s for n greater than 3, and you can use topological argument to show the existence of finite time blob. Okay, this is but n equals 2 is the energy critical dimension, and the first existence of blob solution was due to Zhang Gongqing, Ding Yue, and Ye Gang in 1991 for boundary value problem. So they reduce the Harmonic Map flow to a scalar parabolic equation, and they studied the boundary value problem, and they use the sub and shift solution to show that the solution must blob. Okay? And in 2013, Rafa and Schur, they construct this scalar equation, parabolic equation, but for Cauchy problem. So this is the Cauchy problem, and they found the precise blob rate, which is log square over t minus t. So we started this problem quite a long time ago, but we finished like in 2018. So so in general domain case, in general domain, yeah, and with multiple blobs, okay. So with Davina and Manuel de Pino, we have a general theory, which I'm going to present later, for the construction of general blobs in general domains. So the first result we have is, given any k points and given any time, okay, small time, we can find an initial data, we can find a boundary data, so that the solution, okay, to the Harmonic Map flow blows up precisely at these k points, and the blob rate is a log square over t minus t. And furthermore, the blob is co-dimension k stable. Okay, so for example, if k equal 1, it means co-dimension 1 stable. So we have the solution is almost stable. The blob solution is almost stable. And after we have the first blob, and so the next question is, can we continue the blob? And the answer is yes. And we prove in the same paper that you can continue the blob without changing the topology of your solution. And so so the blob profile will be for t less than capital T is a log square of t greater than minus t. But for t greater than capital T, you can just add a reverse bubble, okay, which is log square over little t minus big T. So you can somehow continue the bubble. So pass the blob time, and you can attach another bubble. So this is this kind of reverse bubbling was the first constructed by Topi in 2004. Okay, and there's another kind of bubbling, which is a spontaneous bubble, which is when t less than capital T, you don't have a bubble, so the solution is smooth and nice. But then you can attach a bubble for t greater than capital T, and the blob rate will be log over t minus t. So are there some questions in the chat?
Yes, I can read it. Does the energy decrease discontinuously at t? Is the question.
Okay. Yes. So the first, this solution, the energy will be continuous. Okay. So that's why this continuation of a block. But this one, you have a continuous, discontinuous. The energy will be discontinuous. This energy will be discontinuous. But this energy will be continuous. Yeah. So that's a continuation of the blob. You have the same energy when t less than capital T, and the same energy for t greater than capital T. But for this, you have a jump in the energy. So these three results shows that you start with any initial data, you have infinite many weak solutions, right? Infinite many global weak solutions, because you can just have a bubble and then attach a bubble, or just you can have a spontaneous bubble any place, anywhere, any place. So you can just simply cook up infinite many weak solutions, right? So this is quite interesting, because now, so this existence of infinite many weak solution, you prove this by growing the bubbles, right? By growing any bubble. I see another question in the chat. Well,
it was a thank you.
Well, thank you. Okay. So let me just summarize. So we have three results, which is forward bubbling. So for t less than capital T, the t goes to capital blob, and reverse bubble for t go to capital blob, and for t greater than capital T, you also have a blob. And we have a spontaneous bubble. So no bubble for t less capital T, and then you have a spontaneous bubble for t greater than capital T. So you have all this kind of phenomena. You can all kinds of solutions you can construct. And the other type of bubble solutions, infinite time blob with the degree 1 harmonic map, and the infinite time blob with the degree 1 harmonic map, but the different blob rate. One is one is quotient problem, another one is the condition problem. And you also have infinite time blob with the degree 2. And in R3, in dimension 3, you can have another type of new type blob, which are the shrinking rings, which have like a point blob, but the point is actually a ring. It's a very small ring. The size of ring is like square root of t minus t, which is a similar size, and the blob rate is like the two-dimensional blob rate. So you found a point singularity in R3 for harmonic map in R3, and which has the same blob rate as a two-dimensional blob rate. Okay, so I want to introduce give a brief introduction the proof, because I'm going to use this for later constructions. So the proof is by so-called inner outer green scheme. So we start with the stationary harmonic map, and you can write down the degree 1 stationary harmonic map precisely, and you have scaling environments and the translation environments and rotation environments. Since we are doing the general case, we have to consider all environments. So you have all these 6 environments. So you have 3 rotations and 1 scaling and 2 translations. So in total, you have 6, right? 6 parameters. So our solution is basically a 6 parameter of solution plus I outside a noise. So this noise is the U infinity. We call it U infinity, right? It's the U infinity. And the general description of a blob. Yes?
There's a question in the chat. What is the definition of the degree here? I assume on the previous slide.
Yeah. This okay. Okay. there's a degree, there's a definition of the degree, right, in R2 for any harmonic map, and this is a degree 1. Right? So it's ux wedge uy, and you integrate in R2, and this is the degree. So and this is the degree 1. All degree 1 solutions are just a Mobius transform of this one, but the high degree solution, which we're not considering. So our general solution is just the 6-parameter degree 1 solution plus I heat equation, a solution for the heat equation. So this is our solution. Our solution is very simple. Okay. So it's the degree 1 harmonic map plus the solution for the heat equation. And so the solution for the heat equation provides like the trajectory of the blob, okay, the bubble location, and also provides the non-local ODE for the scaling parameter and for the rotation around the Z. And this non-local ODE can only be solved if the right-hand side satisfies some condition, which is the outside noise must vanish at this point and the divergence should be positive. Now, this condition is a generalized Zhang-Ding-Ye condition. Zhang-Ding-Ye condition is for the co-rotational condition, and this is the Zhang-Ding-Ye condition in the general case, in the general domain, in the general data case. So so this non-local ODE also provides as instability. Okay, so this non-local ODE is unstable in the rotation direction. So that's why the blob is in general is not stable, is co-dimension K stable. If one bubble is co-dimension 1 stable. So that's how the blob, the instability of a blob comes, is because of the rotation in the Z direction. And the rotation in the X and the Y, they stay bounded. So they also have an equation for this stay bounded. So these are the general form of the solution and the dynamics of these 6 parameters. Okay, so how do we show that? How to prove the existence of such a solution? So the proof is by in the outer green. So I will just give a very brief introduction on this method. So the idea is to define, this is a singularity formation problem, and the idea is to divide your problem into 2 problems. One is the inner problem, which is only solved near the singularity, and you capture all the essential information of the singularity. And the outer problem, which is solved in the whole space, and some all global and external effects. So this approach, in the outer approach for parabolic, has been developed by Kataza, De Pino, and Musso for the Fujita equation, and by Davina, De Pino, and myself for the Harmonic Map Flow. Okay, so let me just explain the main idea and the main difficulty. So this is our harmonic map equation, and we're looking for a solution like this. Okay, degree 1 harmonic map with 6 parameters. Right? Okay, and so the idea is very simple. We linearize around this U0, and we construct a solution with a small perturbation type. So we linearize around U0, and we get a linearized equation. And it's a harmonic map flow is a system, so it's a little bit complicated, but still you can write down all the computations. So the key idea of in the outer green is to see how we construct this error. So we construct this the perturbation by inner and outer. So we cut the inner in close to the block place, and then we construct a solution to the outer problem. So what is this inner problem? What is this outer problem? So the inner problem, the phi only solves the inner problem, but only solve very close to the block point. Okay, we only solve this inner problem very close to the block point, and the outer problem will summarize all the error you have. Okay, because of that. Right. So this is the inner outer system. And so basically the inner problem is linearized around the degree 1 harmonic map, and the outer problem enter into the inner problem by this potential, shorting a potential. Okay. Now the inner problem enters into the outer problem by the cutoff function, because you cut near the block point, so you have this cutoff function. Okay. So this is how the inner outer decouple. The outer problem enter into this potential. The inner problem enter into outer problem through this cutoff function. So we need to understand the effect of this cutoff function. Okay, so let's look at the inner problem. So we use the inner variable. Okay, and in the inner variable, our approximation will be just the degree 1 harmonic map, and so the inner problem will become a linearized problem around the degree 1 harmonic map, and plus some error of some operator on the outer problem and the small nonlinear terms. So okay, so now for the grouping to work, the most important thing is for the inner problem, we need to find an inner solution which has fast spatial decay and fast time decay. So a model problem is the following. This is the model problem. So let's consider a Schrödinger type linear the parabolic equation, and let's suppose our error has both a space decay and a time decay. Okay, so the question is, can we find a solution to this linear parabolic problem which has both space decay and the time decay, at least inside the subsimilar regime? Okay, inside the elliptical regime. Now, so this is a simple problem. This is what we need to solve. Okay, and so if we don't have the time variable, and this is elliptical theory, and you can find a decay solution by Friedholm using some compactness argument. Right, you can do weighted solving space and the compactness argument. Of course, then you need some kind of orthogonality condition, because this linearized operator may have kernel, and then you need to orthogonal H will be orthogonal to the kernel of this elliptical problem. But for parabolic problem, we don't have a freedom theory. So that's the main problem. We need to get sort of parabolic freedom theory for this linear parabolic problem. And our problem is worse than that. And the reason is that we have 6-dimensional kernel, and the only 2 kernels which correspond to translations are in L2. Okay, and all the other kernels are not even in L2. So for parabolic problem, if you have L2 theory, you can use L2 theory to replace the Friedholm, right? You can use L2 theory. But only the translations are in L2. All other kernels are not L2. And this is the main problem, right? So you don't have L2. How do you do a parabolic problem? Right? How do you do the parabolic problem? So the main problem is this scaling parameter and this rotation around Z. They are not in L2. They decay like 1 but they are not in L2. Okay, so if your kernels are in L2, you can have a good theory, sort of freedom theory, as long as your right-hand side is orthogonal to the kernel, and you can you have a solution which is fast decay in space and fast decay in time. You can find a solution with both decay. And the idea, the proof is by blob analysis and the new wear type, right? And since you have L2, so after shoot for blob, and you're going to get an ancient solution for the linearized operator. So you need to classify the ancient solution for the linearized operator, and because you have L2 theory, you can do a classification. And then after blob away from the singularity, you're going to get a removable a singularity problem for the ancient solution for the heat equation. So you're going to arrive at a heat equation with some singularity, and you need to show that this singularity is removable. So this is a kind of this. So this is the good case. We have L2, and then you can use blob analysis and the new word type of theorem, right? But for mode 0, which corresponds to scaling, and you cannot the kernel is not L2, so you cannot do this kind of blob analysis. And what we did is to use brute force. We really construct a solution to the linearized problem. And this solution lose a lot of time decay inside, but then near the boundary, near the place where you do the blob, you have sort of decay. So this is a problem. We construct this solution by brute force, and you cannot use any blob analysis or new wear type. Okay? So we have all these orthogonality conditions, and this orthogonality condition will give us precisely the equation for the scaling parameter. For example, in the forward blob, and you have a non-local ODE of this type, and we can show that generically the solution to this non-local ODE are given by this order, T minus T over log square. And in the reverse bubbling, you have another type of ODE, which this is, and you can show that it's also like T minus T over log square. And for spontaneous bubbling, and this you also get a non-local ODE, and you show that the generic rate is T minus T over log. So this is a brief introduction of in the outer green and the result on the Harmonic Map. And in the next half hour, I will discuss the application of this green scheme and to other geometrical flows. Are there any questions? Any remarks?
I have a question.
Yeah.
So this works for the sphere, as you explained. If you change the sphere slightly, like something diffeomorphic to the sphere.
Oh, you should work. It will work. Yeah.
It will work. Okay.
Yeah. You just have a potential in front of gradient U square, and it will work.
Exactly.
Yeah.
Okay.
Yeah.
Thanks.
Yeah.
I'm sorry. At the beginning, I had connection issues. Can you briefly say again why inner and why outer? So one works in the domain, the other in the codomain, or did I understand correctly?
Yeah,
I missed the first part.
The inner only works in very close to the singularity. Okay, and the outer works in any domain in the whole space. So it's like you're a doctor, you see some cancer like this, right? You want to just concentrate on this cancer region, right? Okay, do some kind of surgery on the cancer region, and then so the inner part, this is what the inner part is doing. Yeah.
I see. Yeah. Okay. Thank you.
All right. So
sorry.
Yeah.
I mean, at the beginning, you also said that the all this kind of surgeries doesn't change the topology. By this, you mean the degree was always
okay.
Same?
Only for the continuation of blob, you will not change the topology, and all the others you change the topology, right? Because you have a spanness power. Right? Yeah. Initially, you don't have any degree, and then you have a degree. So.
Okay. Yeah. Thanks.
So in the second and the third part, I will discuss the application of this green scheme to Harmonic Map for other geometric flows. The first one is Harmonic Map flow with free boundary. So we can write this like a square root of ut minus Laplace. And another one, the second one is half-harmonic map flow. And as we're going to see that there's a huge difference between these two, even though they're all the statistics are the same. So the first problem arises when we consider the Harmonic Map flow with boundary. So Harmonic Map flow with free boundary. So if you consider the Riemann manifold with some boundary, and the target and your map the boundary, okay, and to a sub manifold of n, okay. So so this is a Harmonic Map flow with a free boundary. Now, this was first studied by Chen Wei and Lin Fanghua in 1998, and they construct many blob examples in high dimensions, and also some blob theorems that was proved. But in low dimensions, the simplest example will be M is R2 and N is R1, for example, okay, or Rn. And in this case, they ask if there's finite time blob, because in that case, the problem is that this is completely non-local, and so you cannot reduce this to scalar parabolic equation. So the Zhang-Ding method cannot be applied, and so you cannot use the scalar equation method. So let's look at the simplest case where M is R2. So the boundary is the half space, and N is R2, and the sigma is S1. So we have this parabolic equation. Is harmonic on the half space, is parabolic on the half space, and then on the boundary you have a Neumann boundary, you have some kind of Neumann boundary condition. Okay, so the stationary of this problem is the half harmonic map, okay, from R to S1, and this has been intensively studied in the last 10 years. The classification of a stationary half harmonic maps by Minot and Sarah, and then for the non-degenerative half-harmonic maps, and we have the result for degree 1, and the Netherman and Shikara, they proved the non-degeneracy for general degree, but with the map U is e to the I d theta, and recently we have a complete non-degeneracy result for any degree, and for any half-harmonic map. So now let's look at the degree one map. You can write down the degree one half-harmonic map, which is nothing but a stereographic projection, and you have translations and the rotations. So the first result I did with Yannick, Sarah, and Juncheng is a finite time blob. So this will have a finite time blob, and the blob rate is exactly like the two-dimensional case. It's t minus t over log square. And in fact, we use the same in the outer green in the harmonic map to construct this harmonic map with the boundary. So this is really like a two-dimensional harmonic map, even though it's a half-harmonic map, sort of half-harmonic map. Now, the second problem, let's look at the true half-harmonic map flow. The true half-harmonic map flow will be ut equals square root of Laplace, plus some Lagrange multiplier times u. So this is the lowest, the other dimensional harmonic map flow with critical scaling. And there have been many results on the regularity of these solutions, like Danilo and Revere, and they have some fundamental results on the regularity of these half-harmonic maps. And Mino and Sarah and Shikara in 2012, and he has the regularity for any other dimensional, okay, including so these are the higher order fractional maps, harmonic maps. And there was a recent result by Winston discussed the regularity of this type of harmonic map. So the equivalent using the Caffarelli surface extension. So this is the equivalent form of the half-harmonic map. So now the only thing is difference from the previous one is the UT is now downstairs. UT is on the boundary. In the previous example, UT is upstairs. Now here UT is downstairs. And so the points of this harmonic map, half-harmonic map, they are related to minimum surface with free boundary. This is has been studied by Fraser and Sean, so I will not discuss this. So the question is, can we have finite time blob for half-harmonic map flow, like the harmonic map flow? And first, the answer seems to be no. So with Yannick Serra and Yongquan Zheng, and actually we construct solutions to the half-harmonic map flow, which blows up at the infinity, and the blob rate is like exponential. So we have our construction actually suggests that for half-harmonic map in R1, the infinite time blob should occur, not a finite time blob. But this is, I think this is a quite interesting problem, So let me summarize for the half-harmonic map. For the half-harmonic map, if your UT is upstairs, so this will be harmonic map with a free boundary. Then you have finite time blob. But if your UT is downstairs, it's like this half-harmonic map, and then you have an infinite time blob. So really, our construction really shows a difference which where you put your parabolic part. If you put a parabolic part up, then you have finite time blob. If you put a parabolic part down, then you should expect infinite time blob. So this is the result on the half-harmonic map flow, and the proof is in the outer green. But now since we have a non-local problem, so we can no longer do this cutoff function, and okay, but you can still extend the in the outer green to the half-harmonic map. So this and to get a construction. So both you have finite time blob, and you also have do the infinite time blob. Okay, so this is the second part of my talk. Are there any questions on half-harmonic map flows?
I have a question, if I could.
Yeah. Yeah.
So distinguishing between these two cases, the first for the derivatives in the equation and the second with the derivatives in the boundary condition.
Yeah.
I guess both of these are gradient flows. And
yes.
The distinction is in the metric, whether one of the metrics is basically bulk or interfacial.
I don't understand what you how does UT related to the metric? I don't. Yeah.
No. I mean, again, if it's a gradient flow, I was looking for you to identify.
For the steady states, they are the same. Okay, they have.
The steady states, but as an evolution in terms of
as an evolution. Yeah. Yes. Yeah. So this one you should have a bulk inside with the standard metric. Yeah. And this one, everything is on the boundary. You only have the boundary. Yeah. Are there any other remarks? So we have this. I think this is in the outer green for the fractional problems, and so the last part I'm going to talk about is recent work, some on YAMLs, and I think it's quite exciting, quite interesting. So what is YAMLs? Okay, so let's consider it from E to M be a factor bundle with a structure Lie group, and so the YAMLs is a capture equation, and so you consider FA is the capture, and the DA star is the cofinite differential. So YAMLs is the gradient flow of the YAMLs function, YAMLs function. So for this problem, this is a classical problem, and for the steady state, Torps and established the Morse theory for the YAMLs functional, and Gang Tian proved that the block set. This for the steady state, for the YAMLs steady state equation, and the block set is Hausdorff dimension n-4 rectifiable, and he was proof the energy density identity, and under some conditions, on the limiting connection, then you can show that this by Tau and Tian, they show that the limit set, the rectifiable set, must have mean capture equal 0. So some sort of kind of minimum surface of codimension 4. Right? And recently, Neighbor and Fortora, they showed the energy density can be computed explicitly as sum of bubble energies. So this is a bubble. This is like true energy identity. So this is the steady state problem in dimension 4. Now, for the YAMLs flow, if dimension is not 4, in dimension 2 and 3, there are global existence and the uniqueness by Ryder in 1992. And in dimension n greater than 4, you can construct finite time block easily by topological argument. This is by NATO. So the really interesting case is dimension 4, which is like the critical. This is the critical dimension. It's like the Harmonic Map Flow. Dimension 4 is the critical dimension. So in dimension 4, Wei in 1994 and prove a global weak solution with finite many point singularities. And so this is the analog of the Harmonic Map Flow in dimension 2. So so you have global weak solution for the YAMLs. And Shanata in 1997 gave the exact formulation and a proof of block analysis and the non-time behavior of YAMLs flow in the Schul's theorem. So the asymptotic behavior and the structure of single cell for Yang-Mills heat flow in dimension greater than 4 was analyzed by Hong and Tian in 2004. So in dimension 4, what about global existence? So Shinata in 1996 proved the global existence for the 4-dimensional Yang-Mills heat flow for small data, okay, small initial data. And the global existence for the any initial data, large data, and this was established by a beautiful paper, by very interesting paper by Warden in 2019. And he proved that the Yang-Mills flow is always global existence for any initial data. Okay, so what we want to understand, okay, so now we know the solution exists globally. And we want to understand what is the non-time behavior of Yang-Mills heat flow in 4 dimensions. Do we have singularity at infinity when the solution blows up at the infinity? So this Shinata and Wei in 1998 showed the Yang-Mills heat flow in the equivariant case, which you can reduce to a scalar equation in a bounded ball, in a ball and with a smooth solution for any time. Okay. And so this is so this is quite different from the Harmonic Map Flow, because for Harmonic Map Flow, if you consider bounded value problem, Zhang year and they showed that the solution may block, okay, may block in finite time. But for Yang-Mills, the solution will not block, and they exist infinite time. And Whiten, in his PhD thesis in 2014, and showed that this solution concept by Shinata and Wei has infinite time block, okay, at the infinite. So this is the first infinite time block for the Yang-Mills heat flow. So what we're interested is construction of an infinite time block for the Yang-Mills heat flow with general initial data and without any symmetry assumption. So for the without the SO4 equivalent condition. And we want to study the stability of this infinite time block. Okay, so what is our profile? Like in the Harmonic Map, we have the decaying Harmonic Map. So in the Yang-Mills, we use the ADHM soliton. So first introduce the so-called quaternion and the linear algebra and the self-dual form. So this is ADHM instance are steady states of the Harmonic Map of the Yang-Mills, and they are given explicitly. This is the connection, the matrix. Right? This is the instant, which is explicit. Okay, this is the first Yang-Mills soliton. Okay, the Yang-Mills soliton, and we're going to use this soliton to construct infinite time block. And so all this can be computed explicitly. Now, this ADHM instant, they have actually 5 parameters. They have 4 translations and 1 scaling. So these are the 5 parameters of solutions. And Artia and H and Singer, they prove that this modular the gauge. So there's a huge gauge which is infinite dimensional. Modular gauge and this instanton is stable. Okay, this instanton is stable. So our result, our first result for Yang state flow is existence for infantile blob, but without any symmetry assumption for general initial data. So we construct a solution, a general initial data, and we found a blob, infantile blob solution, which is like the 5-parameter solution of the instanton and plus perturbation, and this scaling parameter lambda goes to 0 exponentially. So this is an infantile blob, and in the general initial data, and this blob actually is stable. Okay, so nearby you also have this kind of infantile blob. So this is and we don't assume any symmetry for this construct. So the solution we constructed, they have the same form like in the Shinata or Shinata's 1997, and recently there's also a construction of infantile blob for the hyperbolic Yang by O and Tataro, and it appeared in Annals, and they use the same this ADHM instant, and you have the same proper behavior for the connection Now, the second type of result I think is quite interesting, which is new. It's a bubble tower for the Yang mills. So, bubble tower solution was constructed for Fujita heat equation or for the wave maps. But for Yang mills heat flow is not known, even for the radial symmetry, even for the equivariant case. So here we give the first existence of a bubble tower for the Yang mills. And so this is a superposition of two instantons. The first instanton is the blob that is like 1 over lambda 1 square, and the second one is like 1 over lambda 2 square. And interesting, the first one blows up like an exponential, okay. But the bubble tower, the second bubble, blows up with a double exponential, and it's very, very singular, which is the growth of like exponential to the minus exponential. So it's really, and these are the singularity at infinity. So you have a bubble tower with 2 bubbles. We just did 2 bubbles, but you can generalize to arbitrary bubbles. But then for arbitrary number of bubbles, you're going to get triple exponentials, and these are too complicated. So we're not, yeah. So this will be the first the bubble tower, the existence bubble tower for the Yang mills, even for in the SO4 equivariant case. Okay, let me just give an outline of the proof. Are there any questions, remarks?
Yes,
Yeah.
This is just with the gauge group SU2 or SU2 times SU2?
Just SU2, R4, just SU2, yeah.
Because they become, the equations are non-linear, and you have the sum of 2 solutions.
Yeah. And yeah, okay. I should say, yeah, this should be, you should take a matrix and multiple. Okay, I should say it's not. So formally, it should be, yeah. Okay, I should be careful with this. Yeah, it's just this. Yeah. You cannot. Yeah. Okay, I should say that.
Okay.
You should do a multiple of the matrix. Yeah. So
Okay,
what is new ingredients of the construction is the to apply the inner outer green for the YAMLs. The main problem is the gauge, right? As everyone knows, YAMLs, the problem is the gauge. Once you can deal with the gauge, then you can use minimum elliptic or parabolic method. So the in general, the YAMLs, if you just because the gauge environments, the YAMLs is not elliptic. So you have to restrict yourself to certain gauge. Okay. So what is we found a very nice gauge by Donaldson and De Turck. We call Donaldson-De Turck. And this De Turck trick is to find a gauge in the same time we solve the YAMLs. So the gauge is solved by using the YAMLs flow. And so this using this De Turck trick, and this actually was first used by Wei, also in the famous paper in 1994, the De Turck trick. Using this De Turck trick, our operator will become our equation will become elliptic or parabolic. So this is our approximate solution, and we have a scaling parameter, we have a translation parameter, and we also have a rotation parameter. And this rotation parameter corresponds to the gauge, to certain gauge. We have to choose a certain gauge. So, and we found that found all the kernels, which is with the decay, 8-dimensional kernels, and then we get 8 dynamic systems. Okay, like the dilation and the translation, and then the gauge invariance, and this is the rotation, and the rotation, and also solve some OD. Okay, so I will not talk. I think my time is almost up. So I will maybe now go to the bubble tower construction, because the bubble tower I think is quite interesting. The growing. So let's look at the equivalent case. SU4, the YAMLs just become a scalar equation, parabolic equation, and the steady state is the standard ADHM okay, standard HM instant. So if we do this transformation, and this become almost like a 6-dimensional critical heat equation. Okay, so the whole idea of a bubble tower is with those. The reason that the bubble tower is so difficult because one grows exponential, another one grows double exponential. So it's really that you cannot mix these two, because this two blow-up is just not comparable. So our idea is to first use the one bubble solution we constructed before, and then in the one bubble solution, we put another bubble, and we call it mu3, and then we compute the equation for mu3. Now, but when you do this, then you need to adjust this one bubble solution. But this one bubble solution, you already constructed the one bubble solution. So how do we adjust this one bubble solution? Is okay. So what we do is to introduce an artificial Lagrange multiplier, which are related to the one bubble solution, and then using this artificial Lagrange multiplier and to do the linear theory. So we have an inner problem and outer problem. Now the outer problem is also singular. The outer problem contains bubbles, and so we need to restrict. We need to even for the outer problem, we need to divide into the inner and the outer and do the reduction. So this is I think my time is up. and there's a lot of computations. But so the main takeaway message today is in the outer green and apply to geometric flows, harmonic map flows, half-harmonic map flows, and the Yang-Mills flows, and you can construct all this type of blob solutions, finite time and infinite time. And my hope is this method can also be used to analyze the flow, do a reverse construction, the reverse in the outer green, and that will be interesting. Yeah. Okay, thank you.
Thank you very much. My